A cataclysm unfolds in the silent void between galaxies. Two dead stars, each a city-sized remnant of a stellar giant, slam together in a final, violent embrace. This event, a neutron-star collision, is one of the most powerful explosions in the universe, yet its true value is not just in its raw power, but in its secrets. These mergers act as cosmic laboratories, creating conditions of density and pressure so extreme they are impossible to replicate anywhere on Earth. By watching them, we are conducting fundamental physics experiments on a galactic scale. By the end of this journey, you will understand how these distant cataclysms are rewriting the rulebook for matter itself. We will uncover where the gold in your jewelry truly comes from, and probe the mysterious state of matter at the very heart of a neutron star. This is a story that connects the death of stars to the fabric of reality. What does it feel like to witness the universe perform an experiment we could never build ourselves to understand the impossible matter these collisions create? We first need to understand the furnace that forges it. It begins with a star not like our gentle sun, but a true titan many times more massive. For millions of years, this giant burns through its nuclear fuel in a fierce battle, fusion pushing outward against the immense gravity pulling inward. This balance defines a star's life, but for a massive star, this story has a spectacular and violent final chapter. When its fuel finally runs out, gravity wins the war in an instant. The star's core collapses catastrophically, triggering a supernova explosion that outshines entire galaxies. What remains after that unimaginable blast is not nothing. It is the star's heart crushed beyond recognition. All the mass of a body larger than our sun is compressed by its own gravity into a sphere no wider than a city. This is a neutron star. The numbers defy belief. A single sugar cube-sized piece of this material would weigh as much as every person on Earth combined. The gravity at its surface is so strong that if you could drop a marble from just a meter high, it would hit the ground at nearly the speed of light. Under this crushing pressure, matter itself breaks down. The atoms that make up everything we know are squeezed until their structure vanishes. Electrons are forced into protons, and together they transform into neutrons. The entire star becomes a sea of these subatomic particles, a state of matter so extreme it is called degenerate matter. It is no longer a solid, liquid, or gas. It is something entirely alien, a perfect, frictionless fluid of pure neutrons held together by the most intense gravity in the cosmos. This is the raw ingredient. This is the impossible substance waiting in the dark, and when two of these unfathomable objects are set on a collision course, the universe prepares its most extreme laboratory. But a single neutron star is only half the story. For the ultimate cosmic experiment, you need two, and the universe, in its vast and patient creativity, often provides. Across the galaxy, pairs of these stellar corpses are locked in a silent, slow-motion dance. This is a binary neutron star system. Two city-sized spheres of degenerate matter, each more massive than our sun, orbit a common center of gravity. They are separated by a distance not much greater than that between Earth and the Moon, yet they are bound together by a gravitational pull so fierce it warps the very fabric of space and time around them. Their dance is not a stable one. According to Einstein's theory of general relativity, such massive objects in a tight orbit should not simply coast forever. As they move, they ripple the space-time around them like stones spinning in a pond, sending out waves of gravitational energy. These are gravitational waves, literal vibrations in the structure of the cosmos. With every wave that radiates away, the binary pair loses a tiny amount of orbital energy. This loss is minuscule, but over millions of years its effect is relentless and inescapable. The two stars begin to spiral inward, drawing closer together with each passing orbit. This long, slow process is called the inspiral. It is a death spiral set to a cosmic timescale. Their orbits tighten, their speed increases, and the gravitational waves they emit grow stronger and faster, like a silent siren rising in pitch. For eons, this dance continues, a predestined countdown written into the geometry of the universe itself. There is no stopping it, no last-minute reprieve. The mathematics of general relativity chart their course with perfect certainty. They will continue to spiral inward until, finally, their immense gravity overcomes the last vestige of distance between them. The final orbits take mere milliseconds, and then they collide. This merger is not a random accident. It is the predictable, cataclysmic endpoint of a dance that began when ancient stars died. It is a scheduled detonation in the cosmic laboratory, and we have only just learned how to read the invitation. The final milliseconds are a blur of cosmic violence. The two neutron stars, each a perfect sphere of degenerate matter, do not simply crash. They are stretched into teardrop shapes by the other's immense gravity, their surfaces erupting in tidal waves of pure neutron, fluid hundreds of meters high. In the last instant before contact, they are whipping around each other thousands of times per second, a dizzying pirouette that ends not with a bang but a splash. They touch, and their outer layers merge into a single, seething, donut-shaped mass of hyper-dense material. The energy released in this moment is staggering. The gravitational wave signal, which had been a rising chirp for millions of years, reaches its crescendo and then abruptly cuts off. The dance is over. But the experiment has just begun. This merger creates something entirely new and violently unstable. The combined object, for a fleeting moment, may form a supermassive neutron star or collapse directly into a black hole. Regardless, the collision flings a significant portion of the neutron-rich material out into space at incredible speeds. This ejected shrapnel, still under intense heat and pressure, is where the true magic happens. As it expands, the conditions become perfect for a rapid series of nuclear reactions unlike any seen in a supernova. This is the kilonova. Think of a kilonova as the universe's most efficient and spectacular forge. It is a brief, brilliant flash of light that can outshine entire galaxies for a few days, but its signature is distinct. While a supernova is powered by the decay of radioactive nickel and shines with a hot, blue-white light, a kilonova's glow is cooler and redder, laced with the unique fingerprints of heavy elements. This is because the neutron-rich environment allows atoms to capture free neutrons at an astonishing rate, building up heavier and heavier nuclei in a process called the rapid neutron capture process, or the R process. It is in this expanding cloud of stellar debris that the universe manufactures elements like gold, platinum, and uranium. The gold in a wedding ring or the platinum in a catalytic converter was almost certainly forged in the violent aftermath of a neutron star collision, a kilonova's fleeting signature written into the periodic table. The laboratory is now fully operational, its first results streaming out across the cosmos as light. That brilliant, reddened glow of a kilonova is more than just a cosmic light show, it is a chemical fingerprint. For decades, astronomers had a fundamental puzzle. They knew the universe created light elements like hydrogen and helium in the Big Bang, and that stars forge elements up to iron in their cores through steady fusion. But the origin of the heaviest elements, the ones with large, complex nuclei like gold, platinum, and uranium, was a mystery. The conditions needed to build them were simply too extreme for ordinary stars. The kilonova provided the missing crime scene. The ejected material from the collision is a physicist's dream and an atom's nightmare. It is an intensely hot, expanding cloud absolutely flooded with free neutrons, the building blocks ripped from the hearts of the colliding stars. In this environment, normal rules of atomic stability are suspended. An atomic nucleus, like a seed, finds itself in a torrential rain of neutrons. It can capture them faster than it can naturally decay, a runaway process that builds heavier and heavier elements in a matter of seconds. This is the rapid neutron capture process, or the R process. It is cosmic alchemy happening at breakneck speed, transforming the simple, neutron-rich debris into a periodic table's worth of heavy elements. The proof was written in the light itself. When astronomers finally captured the detailed spectrum of light from a kilonova in 2017, they didn't just see a generic glow. They saw the specific, telltale absorption lines of heavy elements like strontium and cesium being forged in real time. The data revealed a cloud expanding at a significant fraction of the speed of light, laced with material many times the mass of our entire planet, all freshly minted into precious metals and radioactive elements. This confirmed that neutron-star collisions are not just one source of heavy elements, they are likely the universe's primary forge for gold and platinum. So the ring on your finger or the circuitry in your phone contains atoms that were born in a cataclysm of unimaginable violence, a testament to a forge that operates under impossible conditions. Yet the Kilanova's forge only tells us about the debris flung into space. To uncover the deepest secrets of matter, we must look past the explosion and back toward its source, into the heart of the collision itself. Within the merging cores, conditions become even more extreme, reaching pressures and densities that make the outer neutron sea seem almost tame. Here, physics enters a realm of pure theory, where our understanding of the fundamental forces begins to fray. The central mystery is stark: what happens to matter when it is squeezed to several times the density of an atomic nucleus? A neutron star is not a uniform ball. Think of it as a cosmic onion with layers of increasing strangeness. The outermost layer is a solid crust, a crystalline lattice of atomic nuclei so dense they are packed almost shoulder to shoulder, swimming in a sea of free electrons. Just a few hundred meters down, the pressure becomes so immense that even these nuclei are crushed. This is where we find the neutron ocean, that degenerate fluid of pure neutrons we described earlier. But even this is not the final frontier. As we push toward the very center, the density soars to values that are almost meaningless to articulate. Under this incomprehensible pressure, the neutrons themselves may not survive. They could dissolve into their constituent parts, quarks, creating a bizarre soup of free quarks and gluons known as quark matter. Or perhaps they transform into exotic particles like hyperons. Some theories even suggest the formation of a superfluid, a frictionless state that could rotate independently from the star's crust, creating glitches in its spin. We simply do not know. The equations of quantum chromodynamics, which govern the strong nuclear force, become impossibly difficult to solve under these conditions. Our most powerful particle colliders on Earth can only create these densities for a fleeting moment in a volume smaller than a single proton. A neutron star's core, in contrast, is a permanent, city-sized region of this impossible physics. It is a locked vault, and we have never had the key until now. The violent merger of two neutron stars does not just fling material outward. It sends powerful tremors through the matter in their cores, ringing them like a bell. The frequency and decay of these tremors, encoded in the gravitational waves and the light of the kilonova, carry direct information about the internal structure of the stars. How stiff or soft is this ultra-dense matter? Does it resist compression fiercely, or does it yield easily? The answer tells us what the core is made of. By observing the final moments of the collision, we are, for the first time, placing observational constraints on the universe's most extreme state of matter. We are beginning to listen to the echoes from inside the vault. This ultimate state of matter is governed by a single, elusive set of rules. Physicists call it the equation of state. Think of it as matter's ultimate rulebook, a fundamental relationship that describes how any substance responds to the most extreme conditions imaginable. For something familiar like water or air, we know this rulebook well. We can predict how water will turn to steam under heat or how air will compress in a tire. But for the degenerate matter inside a neutron star, this rulebook is mostly blank pages. We are trying to write the final chapters by observing the universe's most violent experiments. The equation of state for neutron star matter is the single mathematical relationship that links its unimaginable density to the crushing pressure it exerts. This relationship dictates everything about the star's internal structure. It determines how stiff or soft this exotic material is. A stiff equation of state means the matter strongly resists being squeezed further, resulting in a larger, more massive neutron star that can exist before collapsing into a black hole. A soft equation of state suggests the matter yields more easily to pressure, leading to a smaller, denser star that might transform into something even stranger at its core. This is where the true mystery lies. The unknown equation of state holds the answer to what form matter ultimately takes under these impossible conditions. Does the neutron ocean in the core remain a sea of neutrons all the way to the center? Or does the pressure become so great that the neutrons themselves shatter, dissolving into a soup of their constituent quarks, creating quark matter? Perhaps exotic particles called Hyperons, which contain strange quarks, begin to appear. Each possibility corresponds to a different version of that cosmic rulebook. Determining which one is correct is one of the grandest challenges in modern astrophysics, because we cannot recreate these conditions in any laboratory on Earth. Our particle colliders can only glimpse these states for a minuscule fraction of a second in a space smaller than an atom. We need a natural laboratory that operates on a monumental scale. This is why neutron star collisions are so revolutionary. When two of these objects spiral together and merge, they do not just create a flash of light. They probe the very equation of state we seek. The gravitational waves they emit in their final milliseconds carry a precise imprint of how the stars deform under each other's tidal forces, which depends directly on the stiffness of their internal material. The properties of the resulting kilonova, its brightness and how quickly it evolves, are also shaped by the underlying rules of the ejected matter. Each observed collision is not merely an explosion to catalog. It is a critical data point, a single experimental result from the cosmos that helps us fill in a blank line in that ultimate rulebook. With enough of these data points, we can begin to cross out theories that do not match what the universe shows us, inching closer to understanding the true nature of matter at its absolute limit. The first direct messenger from such a collision arrived not as light, but as a ripple in the fabric of space itself. On August 17, 2017, gravitational-wave observatories named LIGO and Virgo detected a distinctive signal. It was not the brief, thunderous crash of black holes merging. This signal was different. It began as a faint whisper, a wobble in the laser beams of the detectors, and over the course of about 100 seconds, it grew steadily stronger and faster. To the scientists listening, it sounded like a cosmic chirp, rising in both pitch and volume before culminating in a final, messy crash. This was the sound of two neutron stars spiraling together over millions of years, their final orbits compressed into just over a minute and a half of observable data. That chirp was a direct recording of the inspiral, a soundtrack to a dance of death written in the geometry of spacetime. For the first time, we had heard the universe's most extreme laboratory powering up. But this signal was far more than just a spectacular sound. It was a data stream packed with precise physical information. The frequency of the waves told us how fast the objects were orbiting, which revealed their combined mass. The amplitude or loudness of the signal indicated how far away the event was, and the duration of the chirp, how long it took to rise from a whisper to a crescendo, helped pin down the individual masses of the two stars. Yet embedded within that rising tone was an even subtler clue, one that speaks directly to the nature of the matter inside. As the two stars drew closer, their immense gravity didn't just pull them together, it stretched them. Each star raised a tidal bulge on the other, much like the moon raises tides on Earth's oceans, but with unimaginably greater force. This tidal deformation leaves a specific fingerprint on the gravitational wave signal. How much the stars stretch before they merge depends critically on the stiffness of their internal material. Think of it this way. If you have two balls of a very soft, malleable substance like clay, their gravity will pull them into elongated shapes long before they actually touch. But if you have two incredibly rigid ball bearings, they will remain nearly perfect spheres until the instant of collision. The gravitational wave chirp from the inspiral phase carries the imprint of that stretching. By analyzing the subtle ways the waveform deviates from the prediction for two perfect points of mass, physicists can measure the tidal deformability of the stars. This single parameter is a direct window into the equation of state. A high deformability suggests softer, more squeezable matter inside, consistent with certain exotic core compositions. A low deformability points to extremely stiff matter that resists distortion fiercely. That one detection in 2017 provided the first ever measurement of this property from real cosmic data. It immediately began to rule out entire families of theoretical equations of state that predicted matter either too soft or too stiff to match what was observed. Each new chirp we detect from a neutron star collision is not just another event. It is another precise measurement in this grand experiment, another data point helping us write the rulebook for matter under impossible pressure. That gravitational wave chirp was only the beginning of the story. For the first time in history, that signal did not arrive alone. Just 2 seconds after the gravitational waves peaked, a space-based gamma-ray telescope named Fermi detected a short, intense burst of gamma rays coming from the same general patch of sky. This was the trigger. The gravitational wave observatories had provided a rough map, a vast swath of the cosmos where the event occurred. Now, with a gamma-ray burst as a second clue, astronomers around the world knew exactly where to point their telescopes. This was the dawn of multi-messenger astronomy, the ability to observe a single cosmic event through different complementary channels of information. Think of it like witnessing a distant explosion. Before this moment, we could only hear the sound, a gravitational wave chirp telling us something massive had collided. Or we could only see the flash, a burst of gamma rays or a new point of light without knowing its precise origin. On August 17, 2017, we could do both at once. We heard the crash and saw the flash, and they came from the same place. This coordination was the key that unlocked the cosmic laboratory. Within hours, optical telescopes had pinpointed the source in a galaxy called NGC 4993, about 130 million light-years away. What they saw was the Kilonova, evolving exactly as theories had predicted. It started as a hot blue glow and then faded through purple to a deep, reddened crimson over the following days. This was the visual confirmation, the smoking gun. The gravitational waves told us two neutron stars had merged. The light told us that merger had forged a cloud of heavy elements. For the first time, we could directly correlate the dynamics of the collision, encoded in the gravitational waveform, with the chemical output of the forge, written in the Kilonova's light. It was a perfect validation of decades of theoretical work. This single event, known by its catalog number GW170817, transformed astrophysics. It confirmed that short gamma-ray bursts are indeed the birth cries of neutron-star mergers. It proved that these collisions are the primary cosmic factories for the heaviest elements. And most importantly, it demonstrated that gravitational waves and light together provide a complete picture of the most extreme physics in the universe. The cosmic laboratory was no longer a theoretical concept. With GW 170817, it became fully operational, its instruments now synchronized, ready to reveal the secrets of matter written in both the ripples of space and the glow of creation. The subtle distortions in that gravitational wave chirp hold the key to matter's deepest secrets. This is where we learn to read the stiffness of the universe's most extreme substance. When two neutron stars spiral together, their immense gravity doesn't just pull, it stretches. Each star raises a tidal bulge on the other, a literal mountain of ultra-dense material hundreds of meters high, drawn toward its companion. How large that bulge grows and how easily it forms tells us everything about what's inside. Physicists call this property tidal deformability. It is a direct measure of how squeezable a neutron star is, and therefore a direct probe of the equation of state governing its core. Think of it with a simple analogy. Take two balls of fresh clay and bring them close. Their mutual gravity, if it were strong enough, would pull each ball into an elongated, teardrop shape long before they touched. That's because clay is soft and malleable. It deforms easily. Now imagine doing the same with two perfectly rigid ball bearings. They would remain flawless spheres right up until the instant of collision, resisting any distortion. A neutron star's interior is neither clay nor steel, but something far stranger. Its tidal deformability reveals where on that spectrum it falls. This is how we translate a gravitational wave signal into a physics experiment. A softer equation of state means the matter in the star's core yields more readily to pressure. It is, in a sense, squishier. In a binary pair, a star with a soft interior will develop a larger tidal bulge, stretching significantly as its partner approaches. This extra stretching acts like a gravitational brake, sapping orbital energy and causing the stars to merge slightly earlier than they otherwise would. This early merger leaves a specific signature in the gravitational waveform. The chirp rises to its peak a fraction of a second sooner, and its shape is subtly altered. Conversely, a stiffer equation of state means the internal matter fiercely resists compression. The star is more rigid. It maintains its spherical shape much better, developing only a small tidal bulge. It fights the distortion, so the inspiral lasts a tiny bit longer, and the gravitational wave chirp has a slightly different profile. By comparing the precise shape of the detected gravitational waves with millions of theoretical simulations, each using a different assumed equation of state, we can see which models match reality and which do not. The collision detected in 2017, GW 170817, provided the first real data for this test. Its gravitational wave signal was not a perfect match for every theoretical possibility. Immediately, it began to rule out entire families of equations of state that predicted matter that was either too soft or too stiff. Some models, which suggested extremely exotic and squishy cores full of free quarks, predicted a merger that would have happened noticeably earlier than what was observed. Others, which proposed hyper-stiff matter that barely deformed at all, predicted a chirp that lasted too long. The real signal sat in the middle, constraining the possibilities. It told us that the true equation of state for neutron star matter is likely moderately stiff, but not the stiffest imaginable. Each new collision we detect adds another point on the graph, further narrowing the range of what is possible. We are slowly closing in on the universe's own answer, reading the stiffness of impossible matter in the quiet ripples of space-time. The final chirp of gravitational waves marks the moment of collision, but it does not tell us what remains. In the heart of that cataclysm, a new and profoundly unstable object is born. Its fate is the ultimate question of the cosmic experiment, and the answer hinges on a single razor's edge property: mass. The combined mass of the two neutron stars determines whether the universe, for a fleeting moment, creates something even stranger, or whether it immediately succumbs to the ultimate victory of gravity. If the total mass is just below a critical threshold, the merger can produce a hypermassive neutron star. This is a temporary, seething monster. It possesses the mass of nearly 3 suns, crammed into a volume only slightly larger than a single neutron star. It is supported not just by the quantum pressure of degenerate matter, but by its incredibly rapid spin, which can reach over 1,000 rotations per second. This furious rotation provides an outward centrifugal force that helps it stave off gravitational collapse, at least for a little while. We might witness this object as a rapidly spinning magnetar, a neutron star with a magnetic field a quadrillion times stronger than Earth's. Such a magnetar could inject vast amounts of energy into the expanding Kilonova debris, causing it to shine far more brightly and for longer than expected. Its intense magnetic field could also power a sustained X-ray afterglow, a lingering beacon visible for weeks or months after the initial collision. But this hypermassive star lives on borrowed time. It is hot, turbulent, and losing energy rapidly through neutrinos and gravitational waves. Within milliseconds to perhaps a few hours, it will cross the tipping point. Its internal pressure will no longer be able to withstand its own immense weight, and it will undergo a second, silent collapse, vanishing behind the event horizon of a newborn black hole. This delayed collapse would leave a specific signature, a sudden cutoff in any sustained X-ray emission, a quiet confirmation that the central engine has finally been extinguished. If, however, the combined mass of the colliding stars is above that critical threshold from the very beginning, there is no reprieve. The merger does not produce a star at all. The moment the cores touch, the combined object is already too heavy to be supported by any known force. It collapses directly and immediately into a black hole. In this scenario, the Kilonova is powered solely by the material flung out during the collision itself, without any additional energy from a central magnetar. The electromagnetic signature would be fainter and fade more quickly. The gravitational wave signal would also be telling. The characteristic chirp would end abruptly at the moment of merger, with no additional higher frequency ringing that might suggest a briefly stable remnant vibrating like a bell. Identifying which of these fates unfolds is not just academic. It is the key to finding the universe's ultimate speed limit for density. That critical mass threshold is dictated by the equation of state. A stiffer equation of state, with matter that resists compression fiercely, can support a heavier neutron star. It raises the bar for collapse, allowing hypermassive remnants to exist from mergers with greater total mass. A softer equation of state lowers that bar, making immediate collapse more likely. Every collision we observe is a test. By measuring the total mass from the inspiral and then searching for the telltale electromagnetic signs of a lingering central engine, we can effectively weigh the remnant. Did it persist or did it vanish? The answer places a direct measurement on the maximum possible density of stable matter in our universe. It tells us the point at which the cosmic rulebook runs out of pages and gravity writes the final, singular chapter. The brilliant Kilonova is not the only light that escapes this cosmic forge. From the heart of the chaos, something far more focused and deadly emerges. As the swirling debris from the merger settles, a vast amount of material does not escape into space. Instead, it forms a seething, superheated disk of matter, spinning at nearly the speed of light around the newly formed hypermassive neutron star or black hole. This accretion disk is a reservoir of unimaginable energy, and its physics can trigger the universe's most powerful explosions. Friction and magnetic fields within this maelstrom channel some of this material into too narrow, opposing beams that blast outward at over 99.9% the speed of light. These are the jets of a short gamma-ray burst. They are not a diffuse glow like the kilonova, but are collimated like the beam of a cosmic lighthouse, focused into a cone of devastation only a few degrees wide. The energy packed into these jets is staggering. In just a few seconds, a single jet can release more energy than our Sun will produce in its entire 10 billion-year lifetime. If one of these jets were pointed directly at Earth from across the galaxy, we would detect it as a short, intense flash of the highest energy light in the universe, a gamma-ray burst. For decades, these brief, mysterious flashes were one of astronomy's greatest puzzles. Where did such catastrophic power come from? The detection of GW 170817 provided the definitive answer. The gravitational wave chirp told us a neutron star merger had just occurred. 2 seconds later, the Fermi satellite detected a short gamma-ray burst from the same patch of sky. This precise timing was the final, irrefutable link. It confirmed that the merger of two neutron stars is the engine that powers at least some short gamma-ray bursts. This connection transforms how we see these events. A gamma-ray burst is no longer just a random, terrifying flash. It is a specific signal, a beacon that tells us a merger has happened and, crucially, reveals the geometry of the system. Because the jets are so tightly focused, we only see the burst if one of those beams is pointed almost directly at us. This means for every short gamma-ray burst we detect, there are hundreds of similar mergers happening across the universe whose jets are pointed away, invisible to our telescopes. The gravitational wave signal, however, is omnidirectional. It does not care about orientation. By combining the two, we gain a complete picture. The gravitational waves tell us the merger happened and give us the masses and distance. The gamma-ray burst, if we see it, confirms the model and tells us the system produced powerful jets, and that we are looking almost directly down the barrel. The properties of the burst itself, its duration and brightness, provide further clues about the energetics of the accretion disk and the nature of the central remnant. A brighter, longer-lasting afterglow might suggest a hypermassive neutron star lingered, feeding energy into the jet for a time, while a fainter, quicker burst could point to an immediate collapse into a black hole. Each observation is another measurement in the laboratory, helping us map the violent aftermath of the collision and understand the final moments of matter before it vanishes behind an event horizon. The brilliant flash of a kilonova is just the opening sentence of a much longer story. In the days and weeks that follow, this cosmic forge does not simply vanish. It fades, and the precise manner of its fading holds the entire history of the collision within it. Astronomers do not just take a single photograph of this event. They watch it night after night, measuring its brightness in different colors of light. This meticulous record is called a light curve, and it is the most powerful forensic tool we have for dissecting what the merger created. Think of a light curve as a patient's chart in a cosmic hospital. It tracks the vital signs of the explosion over time. The brightness is the fever, spiking high and then gradually receding. The color is the telltale symptom, shifting from the hot blue of a severe infection to the cooler red of a slow recovery. By reading this chart, we can diagnose what elements are present in the ejecta, estimate their total mass, and even calculate how fast they were blasted into space. It all comes down to radioactive decay and expansion. In the first hours after the merger, the ejected cloud is unimaginably hot and dense. It glows with a blue-white light, powered by the sheer heat of the collision and the rapid decay of very unstable, neutron-rich nuclei. This is the kilonova's peak, but as the cloud expands at a significant fraction of light speed, it begins to cool rapidly. Different materials within the cloud behave in distinct ways. Lighter elements like strontium or cesium are more transparent. They allow heat from the interior to escape more easily, causing their part of the glow to fade relatively quickly. The heavier elements, however, tell a different story. The lanthanides, a group of rare earth metals forged in the R process, are incredibly opaque. They act like a thick cosmic fog, trapping the heat and radiation inside the expanding cloud. This trapped energy has to slowly leak out, and as it does, it shifts the color of the entire event. The blue light is absorbed and re-emitted as longer, redder wavelengths. So over the course of a few days, the Kilanova's color transforms from blue to purple to a deep crimson red. This dramatic color change is the direct signature of heavy elements being present in vast quantities. The rate of the fading is another critical clue. The light is not powered by fusion like a star, but by the radioactive decay of all those freshly minted, unstable isotopes. It is as if the cloud is filled with trillions of tiny, glowing embers, each burning out on its own schedule. The shape of the light curve's decline directly reflects the half-lives of those dominant radioactive elements. A steeper drop in brightness suggests a preponderance of elements that decay quickly, while a more gradual, lingering glow points to longer-lived isotopes. By matching the observed light curve to sophisticated models that simulate thousands of possible compositions, physicists can essentially weigh the output of the forge. They can determine that a particular collision ejected, for example, several times the mass of Jupiter in pure gold, or a planet's worth of platinum. Every dip and plateau in that fading light is a data point. A slight bump in the infrared weeks later might reveal where a particular clump of slower-moving debris finally became transparent. A persistent X-ray signal could hint at the presence of a central magnetar, still pumping energy into the remnants. This forensic timeline of decay allows us to reconstruct the entire event long after the gravitational waves have faded to silence, reading the detailed inventory of a cosmic catastrophe written in its slowly dimming glow. That fading light carries a hidden code. While the overall color and brightness tell us about the mass and expansion, to read the specific ingredients of this cosmic forge, astronomers must perform a kind of spectral surgery. This is the science of spectroscopy, and it transforms a simple point of light into a detailed chemical fingerprint. Every element in the universe, when heated, absorbs and emits light at very specific, unique wavelengths. Think of it like a cosmic barcode. Sodium street lamps glow with a distinctive yellow. Neon signs blaze with a characteristic red. In the vast, hot cloud of a kilonova, every newly forged atom is doing the same thing, imprinted onto the light as it escapes. Astronomers capture this light and spread it out into a rainbow, a spectrum, but this is no ordinary rainbow. It is crossed with dark lines and bright spikes, a forest of features each telling a story. Dark absorption lines appear when atoms in the cooler outer layers of the expanding cloud absorb specific colors of light from the hotter interior behind them. Bright emission lines flash where atoms in particularly energetic regions emit their own characteristic glow. The precise position of each line in this spectral forest corresponds to a specific atomic transition, an electron jumping between energy levels within a particular element. By matching these lines to laboratory measurements made here on Earth, scientists can identify exactly which elements are present, like reading a list of ingredients on a cosmic package. This is how we move from knowing heavy elements are made to knowing which ones. The Kilonova from GW 170817 provided the first complete spectral readout. As telescopes around the world tracked its evolution, their spectrographs dissected its light. Early on, the spectra showed broad, smooth features, a sign of a hot, dense, and opaque cloud where even light struggled to escape with a clear signature. But as the cloud expanded and cooled, the fog began to clear. The spectral lines sharpened, and there, in the data, was a clear set of absorption lines that matched the element strontium. This was the smoking gun. Strontium is a heavy element far beyond iron on the periodic table. Its presence in such abundance could not be explained by ordinary supernova. It was direct, observational proof that the rapid neutron capture process, the R process, was happening in the ejected debris of that collision. For the first time, we weren't just theorizing about where heavy elements came from. We were watching them be created and identifying them by name. Subsequent analysis revealed hints of other elements like cesium and tellurium. Each spectral line is a direct measurement, allowing physicists to estimate not just what was made, but how much. It confirmed that this single event produced perhaps hundreds of Earth masses of precious metals like gold and platinum, along with vast amounts of radioactive material. Spectroscopy turns the Kilonova from a brilliant mystery into an open book, its pages written in the atomic signatures of creation itself. But how does any matter escape such a crushing grip? The gravitational pull at the heart of a neutron-star merger is almost absolute, a force that should trap everything within its event horizon. The answer lies in a violent ballet of competing powers, where not all material is destined to fall inward. Several distinct mechanisms act like cosmic escape artists, each ripping matter free through a different trick of physics, and each producing a unique chemical signature in the process. The first and most direct method is through sheer gravitational slingshots. As the two stars spiral together in their final milliseconds, they are not solid spheres but fluid bodies stretched into teardrops. The extreme tidal forces can literally pull long, streaming arms of neutron-rich material from their outer layers, flinging them away at incredible speeds without ever allowing them to touch the central maelstrom. These are tidal tails, and they form in the orbital plane like debris sprayed from two merging whirlpools. The matter in these tails experiences less heating and neutron exposure than the material at the core, which influences the specific cocktail of elements it can create. A second, and often more prolific, escape route emerges from the chaos left behind. When the central remnant forms, be it a hypermassive neutron star or a black hole, the material that does not immediately fall in swirls into that furious accretion disk. This disk is not a placid ring. It is a superheated, magnetized vortex where friction and magnetic fields generate tremendous pressure and radiation. This energy can drive powerful winds that blow material off the disk's surface, much like the solar wind streams from our sun, but with incomparably greater force. These disk winds lift matter from the inner regions, carrying it up and away from the gravitational abyss. Crucially, this material has been processed through the intense heat and neutron-rich environment of the disk itself, which alters its composition compared to the tidal tails. Then there is a third, more subtle mechanism, one that relies on the ghostliest particles in the universe. If a hypermassive neutron star survives for even a short time after the merger, its core is a furnace reaching temperatures of trillions of degrees. At these energies, it floods the surrounding space with an immense torrent of neutrinos. These nearly massless particles interact very weakly with matter, but in such staggering numbers, they exert a tangible pressure. This neutrino-driven wind can gently push on the hot, dense matter at the surface of the remnant or the inner edge of the disk, helping to lift it and carry it outward. Because neutrinos can change protons into neutrons and vice versa, this wind fine-tunes the neutron richness of the escaping material, which is the single most important factor determining which heavy elements form. The relative strength of these three escape artists' tidal tails, disk winds, and neutrino-driven winds dictates the final product of the cosmic forge. A merger dominated by tidal tails might produce a lighter overall yield of heavy elements with a different isotopic mix. One with a strong, long-lived hypermassive star and powerful neutrino winds could create an enormous, neutron-rich output, perfect for forging the heaviest elements like gold and platinum. The light we see from a kilonova is the blended signature of all these outflows. By carefully dissecting that light's color, evolution, and spectrum, astrophysicists can work backward to estimate how much material came from each channel. It is a forensic analysis of a cosmic explosion, determining which forces were the most effective escape artists, and therefore what the universe chose to manufacture in that particular, impossible laboratory. The spectral fingerprints from a kilonova reveal what was forged, but they don't tell us the size of the crucible itself. To complete the picture of matter under impossible conditions, we need to know the dimensions of a neutron star. How wide is this city of degenerate matter? The answer is not a single number but a range, and pinning it down has been one of the great observational quests in astrophysics. It requires combining two completely different ways of seeing the universe, listening to the ripples of a collision and reading the flickering light of a solitary, spinning star. Gravitational waves from mergers give us one crucial piece of the puzzle: tidal deformability. This measure of a star's squishiness is intimately related to its size. Think of it like squeezing a stress ball. A larger, more inflated ball will deform more easily under your grip than a small, dense one. Similarly, for a given mass, a neutron star with a larger radius will be more susceptible to tidal stretching from its companion. That subtle imprint on the gravitational wave chirp doesn't just tell us the matter is stiff or soft. It translates directly into a constraint on the star's physical size. The data from collisions like GW170817 began to draw a box on the chart, saying the radius of a typical neutron star must lie within certain limits. But to narrow that box into a precise line, we need a second, independent method. This comes from watching isolated neutron stars, the ones not currently colliding. Some of these stars, known as pulsars, sweep beams of X-rays across our line of sight like cosmic lighthouses. When they accrete matter from a companion star, the gas spirals down and smashes onto the surface at the magnetic poles, creating incredibly hot spots. As the star rotates, these hot spots come in and out of view, causing the X-ray brightness to pulse with a regular rhythm. Scientists can use these pulses in a brilliant piece of cosmic geometry. By modeling how the light from these tiny, scorching hotspots is bent by the star's own immense gravity and redshifted as it struggles to escape, astronomers can estimate both the mass and the radius of the star. It's like measuring the size of a distant coin by carefully studying the flicker of a firefly sitting on its edge. When these two separate lines of evidence, the tidal squeezability from mergers and the X-ray pulse modeling from isolated stars, are brought together, they converge on a remarkable consensus. The data from across the cosmos points to a surprisingly narrow answer. Neutron stars, despite their wildly varying masses and histories, likely all have radii very close to 11 or 12 kilometers. Some studies suggest a range from about 11 to 13 kilometers. To put that in perspective, an object containing 1.4 times the mass of our entire Sun is packed into a sphere the size of a modest city. This is a profound observational result. This narrow range of possible sizes acts like a master key for the equation of state. It immediately rules out entire families of theoretical models. Equations of state that are extremely soft, predicting matter that yields easily to form very small, dense stars with radii under 10 kilometers, are largely inconsistent with the data. Similarly, models that are overly stiff, predicting large, puffy neutron stars with radii over 14 kilometers, are also pushed to the margins. The universe, through its dual messengers of gravitational waves and X-ray light, is telling us that the true rulebook for ultra-dense matter produces objects of a very specific scale. This 11 to 13 kilometer radius is the universe's own design specification for a neutron star. Every new observation, every new chirp from a merger, and every new pulse from a lonely pulsar tightens the constraints further, inching us closer to the single, fundamental equation that describes all matter at its absolute limit. But the true nature of this matter reveals itself through a fundamental cosmic speed limit. Deep within a neutron star's core, where atoms dissolve into a sea of particles, there exists a property more telling than temperature or pressure: the speed of sound. In our everyday world, sound travels through air at a mere fraction of light speed. Even in steel, it is a sluggish crawl by cosmic standards. But in the realm of the impossibly dense, the rules change entirely. The speed of sound is not just a measure of how quickly a vibration travels. It is a direct window into the stiffness of a material, into how fiercely it pushes back when squeezed. A higher sound speed means the material is incredibly stiff. Transmitting pressure changes almost instantly. A lower sound speed indicates a softer, more compressible substance. For decades, physicists theorized that in the ultra-dense heart of a neutron star, the speed of sound might approach the ultimate barrier, the speed of light itself. This is not about breaking physics, but about matter becoming so rigid, so unwilling to be compressed further, that disturbances within it propagate with near-perfect efficiency. Recent analysis of gravitational-wave data from neutron star collisions has provided stunning support for this idea. The measured tidal deformability and the inferred radii of about 12 kilometers point to an equation of state that is remarkably stiff. To create a star that massive yet that compact, the matter at its core cannot be soft or squishy. It must be extraordinarily rigid, resisting additional compression with tremendous force. The mathematics translates this stiffness directly into a sound speed. The data suggests that in the deepest layers, sound may indeed travel at a significant fraction of light speed, perhaps more than half. This is a profound revelation. It tells us that under these impossible conditions, matter transforms into something that behaves less like a familiar substance and more like a perfect, nearly incompressible fluid. The core does not yield easily. It pushes back with a vigor that echoes across the star's structure, defining its maximum possible size and mass. This theoretical limit, written in the speed of a silent vibration, is now being measured by the violent collisions of dead stars, revealing the ultimate resilience of matter when pushed to the edge of existence. This ultimate stiffness may not be the final word on matter's behavior. As we peer deeper into the theoretical abyss, an even stranger possibility emerges. What if, under sufficient pressure, the neutrons themselves cease to exist? This is the hypothesis of a phase transition, a fundamental rearrangement of matter's building blocks more radical than ice melting into water. At densities several times that of an atomic nucleus, the immense forces might literally tear neutrons apart. Each neutron, normally composed of 3 bound quarks held together by gluons, could dissolve. The result would be a seething, primordial soup of free quarks and gluons, a state of matter known as quark-gluon plasma. This is not a plasma like the sun's corona, but something far more exotic, a fluid that existed only in the first microseconds after the Big Bang. In the cold, dense heart of a neutron star merger, this plasma might not even be a chaotic soup. Theorists suggest it could organize into something even more bizarre, a color superconductor, where quarks pair up and flow with zero resistance, creating the most perfect fluid in the cosmos. The existence of such a phase would represent a fundamental shift in the rulebook, a literal change of state for matter under impossible conditions. This transition would leave a dramatic signature on the equation of state. As density increases past the critical point, the matter would suddenly become softer. Imagine compressing a spring. For a while, it resists fiercely, but if it suddenly snapped, it would offer much less resistance. A phase transition from neutrons to quark matter is like that snap. the equation of state would show a pronounced softening at a specific, ultra-high density. This softening would have direct, observable consequences in the final act of a neutron star collision. After the two stars merge, if a hypermassive remnant forms, it does not sit still. It vibrates and oscillates like a struck bell, ringing at specific frequencies determined by its internal structure and the stiffness of its material. These post-merger oscillations are subtle tremors encoded in the gravitational wave signal immediately following the main crash. If the core of this remnant undergoes a phase transition to quark matter, its sudden softening would change the tune. The frequencies of these oscillations would shift in a characteristic way. Certain high-frequency tones might be suppressed, while the overall damping of the vibrations, how quickly the ringing fades, could be altered. Detecting this specific harmonic fingerprint in the gravitational waves is one of the holy grails of this field. It would be direct evidence that we have pushed matter into a regime where the very concept of a proton or neutron vanishes, revealing the quark-gluon soup from which all visible matter once condensed. Each new, louder gravitational wave detection from a merger brings our listening instruments closer to hearing this faint, telltale ring, the sound of matter transforming into its most primordial and perfect form. Yet the transformation may not stop at free quarks. There is another exotic possibility lurking in the mathematics, one where the particles themselves are not torn apart, but are instead replaced by something even stranger. Within the crushing pressure of the core, the familiar neutrons might give way to other members of the particle family, ones that are fleeting ghosts in our laboratories. These are Hyperons. To understand them, we need to step back for a moment. A neutron is a type of baryon, a particle made of three quarks. Specifically, a neutron is two down quarks and one up quark. But the quark family has a third, heavier sibling, known as the strange quark. Hyperons are baryons that contain one or more of these strange quarks. In the conditions of Earth, hyperons are incredibly unstable, decaying into ordinary particles in a fraction of a nanosecond. They are not a part of our stable reality. But inside a neutron star, the rules are rewritten by density. The intense pressure creates an environment where the energy cost of creating a strange quark plummets. At a certain threshold, it might become energetically favorable for some of the neutrons to convert into hyperons. It would be like a crowded room where, under extreme pressure, some people spontaneously transform into a slightly different, heavier form that fits the cramped space more efficiently. The emergence of hyperons or other exotic baryons like delta particles would represent a profound change in the star's composition. This exotic matter would have a dramatic effect on the equation of state, but in the opposite direction of a stiff quark core. Hyperons introduce new ways for the particles to interact, new channels for energy loss. Think of it like the structure of a material. A pure crystal of neutrons might be very rigid, like a well-ordered lattice. But if you start substituting some of those neutrons with different, heavier particles that interact in more complex ways, the overall structure can become softer, more compressible. The presence of hyperons would soften the equation of state. This softening has direct, observable consequences. A softer equation of state means that for a given central pressure, the matter yields more easily. This would result in a neutron star with a smaller maximum possible mass and a more compact size. It would also be more deformable in a binary system, stretching into larger tidal bulges under its companion's gravity. That increased deformability would leave a specific, measurable imprint on the gravitational wave chirp of a collision, causing the inspiral to progress slightly faster. So the hunt for hyperonic matter is not a purely theoretical exercise. It is an observational challenge. By precisely measuring the masses and radii of neutron stars, and by analyzing the tidal effects in mergers, we are directly testing whether these exotic particles exist in nature's most extreme environment. A detection of a very massive neutron star, one approaching or exceeding 2 solar masses, already places severe constraints on Hyperon models, as a soft equation of state often struggles to support such heavy objects. Every new piece of data from a pulsar or a collision helps us decide if the core is a pure neutron fluid, a quark soup, or a menagerie of strange particles that cannot survive anywhere else in the universe. The pressure of the impossible becomes a lens, revealing a particle zoo that otherwise remains hidden from our view. But what if the cosmic laboratory sent a signal before the main event even began? The final gravitational wave chirp and the brilliant Kilonova are the grand finale, but theorists are now asking if the universe provides a subtle preview, a faint electromagnetic whisper in the hours, days, or even years before the stars collide. These are precursor signals, and detecting them would transform our entire approach to these cataclysms. Imagine having an early warning system for the most extreme physics experiments in the cosmos. The concept hinges on the unique environment of a binary neutron star system during its long inspiral phase. As the two stars spiral closer over millennia, their powerful magnetic fields and the sea of charged particles trapped within them begin to interact in increasingly dramatic ways. One promising precursor candidate involves the pulsar wind. A spinning neutron star with a strong magnetic field acts like a cosmic generator, emitting a relentless torrent of high-energy particles, the pulsar wind. In a binary system, this wind constantly slams into the magnetosphere of its companion star. As the orbit tightens, this interaction intensifies. The resulting friction can subtly alter the spin of the stars, a process called spin-down. More intriguingly, the collision of these winds and magnetospheres could channel energy into powerful beams of radio waves or X-rays. We might see this as a periodic flash of light, synchronized with the orbital dance, growing steadily brighter and more frequent as the merger approaches. Another possibility involves direct magnetospheric interaction. When the stars get close enough, their magnetic field lines could literally tangle and reconnect, a process that on the Sun drives solar flares but on a neutron star scale would unleash a staggering burst of energy. This could manifest as a sudden, short-lived flare in X-rays or gamma rays, a single brilliant spike announcing the impending collision days or weeks in advance. Detecting such precursors would be a monumental challenge, as they would be far fainter than the merger itself and require monitoring the right patch of sky at precisely the right time. Yet the payoff would be immense. A confirmed precursor would serve as a celestial alarm clock, giving gravitational-wave observatories and telescopes across the planet a heads-up to point in the right direction, ensuring we capture the entire event from the first electromagnetic flicker to the final gravitational-wave ringdown. Beyond early warning, these signals would be a direct probe of conditions we can never otherwise see. The strength and character of a precursor flare would tell us about the intensity and structure of the neutron star's magnetic fields, which are thought to be key in powering the jets of the subsequent gamma-ray burst. It would reveal the density and behavior of the plasma in the space between the stars, an environment dominated by physics we can only theorize about. Finding a precursor would confirm that the final chapter of a neutron star's life is not a silent spiral, but a dialogue between gravity and magnetism, a conversation we are only just learning how to hear. While gravity and density define the stage, it is magnetism that directs the final, violent act. As the two neutron stars spiral into their final embrace, they bring with them magnetic fields of almost unimaginable power, each one born from the collapsed core of a dead star. In the chaos of the merger, these fields are not just combined, they are amplified to levels that defy comprehension. Through a process called the magnetorotational instability, The furious spinning and shearing motions of the hyperdense fluid can stretch and twist magnetic field lines, transferring the immense rotational energy of the system into magnetic energy. The result is a magnetic field that can be amplified to strengths a quadrillion times stronger than Earth's protective shield. To grasp that scale, if you could bring a speck of this magnetized material anywhere near our planet, its magnetic pull would wipe every credit card and hard drive on the globe from a distance of hundreds of thousands of kilometers. This is not a passive backdrop, it is an active, shaping force in the cosmic laboratory. This ultra-powerful magnetic field becomes the chief engineer of the explosion's aftermath. Its influence is most dramatically seen in the fate of the accretion disk, the swirling mass of debris orbiting the central remnant. Without magnetism, this disk would be a relatively sluggish, viscous donut, slowly feeding material inward. But infused with these intense fields, it transforms into a tightly wound spring of energy. The magnetic fields act like cosmic scaffolding, creating friction and tension within the plasma that drives a more efficient and violent accretion process. More importantly, they provide the mechanism to launch the jets. The field lines, anchored in the spinning disk or the central object, get wound up like the rubber band of a toy airplane. When the tension becomes too great, they snap and reconnect, channeling a focused beam of particles and energy along the rotational axis at nearly the speed of light. This is the birth of the short gamma-ray burst, a beacon of focused destruction powered directly by magnetic coercion. But the magnetic field's role extends beyond powering the jets. It also sculpts the kilonova itself. The expanding cloud of heavy elements is not a perfectly symmetrical sphere. The intense magnetic pressure can shape the ejecta, potentially funneling it into a more equatorial distribution or creating asymmetrical lobes. This shaping influences how we see the event. A magnetically shaped kilonova might appear brighter or dimmer from certain viewing angles, and its light could show a distinct polarization, a subtle twisting of the light waves that signals the presence of a strong, ordered magnetic field. This means the same merger could look slightly different depending on whether we are looking down the barrel of the jet or from the side, all because of the invisible magnetic architecture sculpting the debris. This presents one of the greatest challenges in our cosmic experiments. While we can estimate masses and measure tidal deformability from gravitational waves, the initial strength and geometry of the magnetic field in a merging system is a wild card, a key variable that is currently poorly constrained by observations. Two otherwise identical neutron star mergers could produce dramatically different electromagnetic displays: a brilliant, long-lasting afterglow or a fainter, quicker flash based largely on the hidden magnetic blueprint they brought into the collision. Unlocking this variable is the next frontier. By searching for the telltale signs of magnetic shaping in the light curves and spectra of Kilonova, and by correlating them with the properties gleaned from gravitational waves, we can start to reverse engineer this invisible force. Each new detection helps us understand not just what matter is made of under impossible pressure, but how the universe uses magnetism to choreograph the aftermath of its most extreme experiments. The universe's grand experiments are irreplaceable, but they are not our only window into this dense frontier. Here on Earth, in sprawling facilities of concrete and steel, we are building our own miniature versions of these cosmic conditions. These are nuclear physics laboratories, and their goal is to bridge the staggering gap between what we can calculate and what the cosmos reveals. While we cannot create a stable, city-sized chunk of neutron star matter, we can recreate its hot, fleeting essence for a fraction of a second in a volume smaller than an atom. This is the domain of particle accelerators and heavy ion colliders, like the relativistic heavy ion collider in the United States or the Large Hadron Collider in Europe. In these machines, scientists do not collide individual protons, but entire nuclei of heavy atoms like gold or lead. They accelerate these nuclei to over 99.99% the speed of light and smash them together head-on. For a mere moment, in the heart of that collision, temperatures soar to trillions of degrees and densities reach many times that of an atomic nucleus. In that microscopic fireball, the protons and neutrons melt, their boundaries dissolving into a seething, primordial soup of quarks and gluons. This is the quark-gluon plasma, a state of matter believed to have filled the entire universe in its first microseconds after the Big Bang. By studying this hot, dense plasma, physicists are directly probing the strong nuclear force, the very glue that holds all visible matter together and dictates how it behaves under extreme pressure. These terrestrial experiments provide absolutely crucial data, but for a specific regime. They tell us about matter at extremely high temperatures and at densities a few times that of an atomic nucleus. This is the low-density end of the neutron star equation of state, the conditions you might find in the outer layers of the star or in the violently heated ejecta of a merger. The measurements from these collisions, how the plasma flows, how quickly it cools, how particles emerge from it, provide anchor points for our theoretical models. They tell us how the strong force operates when matter is squeezed and heated to these specific, albeit fleeting, conditions. But this is only one piece of the puzzle. A cold neutron star core is a different beast altogether. It is unimaginably dense, but also incredibly cold, near absolute zero. It is a degenerate quantum fluid, not a hot plasma. Our colliders cannot reach these extreme cold densities, nor can they sustain them. This is where the cosmic and terrestrial laboratories must join forces. The equation of state is not a disconnected set of rules for different situations. It is a single, continuous description of matter from low density to high. The data from heavy ion colliders gives us a firm, experimentally verified starting point for this curve at the hot, lower density end. The observations from neutron star mergers and pulsars provide constraints at the cold, ultra-high density end, the realm of pure degeneracy pressure. The grand challenge for theoretical physicists is to build a single, unified equation of state that seamlessly connects these two bookends. It must start with the validated physics from our Earth-bound experiments and extend, through robust theory, all the way to the crushing densities at the heart of a merger, all while matching the precise masses, radii, and tidal deformabilities measured from the stars themselves. Every new result from a collider refines the starting point. Every new gravitational wave detection tests the extrapolation. It is a constant dialogue between the impossibly small and the unimaginably large, a conversation where the universe provides the ultimate exam and our particle accelerators help us study for it. The challenge of understanding this cosmic forge is not just observational but deeply theoretical. To truly interpret the signals we receive, we must attempt to recreate the event itself inside a supercomputer. This is the daunting frontier of simulation, where physicists try to model the unmodelable. A neutron star merger is arguably the most complex physical event in the universe, a problem that demands we combine physics that are normally studied in isolation. It is not just gravity or fluid dynamics or nuclear physics. It is all of them operating at their absolute extremes and all at once. To build a virtual model of this catastrophe, scientists must run what are called general relativistic magnetohydrodynamic simulations. That imposing term simply means the simulation must obey a specific, interconnected set of rules. First, it must account for the severe warping of spacetime as described by Einstein's theory of general relativity, because the gravity here is so strong it bends the very grid on which the simulation is calculated. Second, it must model the behavior of the neutron star fluid itself, a magnetohydrodynamic plasma where magnetic fields are frozen into the flow and can dictate its motion. Third, it must incorporate a detailed nuclear physics network, tracking thousands of possible reactions as atomic nuclei form and decay in the ejected debris. And fourth, it cannot forget the neutrinos, trillions of which are produced and escape, carrying away energy and subtly changing the composition of the matter. Getting these components to talk to each other accurately, across scales from the event horizon to an expanding cloud light years across, pushes the world's most powerful supercomputers to their limits. A single high-fidelity simulation of the last few milliseconds of a merger can take months to run, consuming millions of processor hours. The goal is to generate a predicted signal, a synthetic gravitational wave chirp, and a theoretical Kilonova light curve. This digital prediction is then held up against the real data from telescopes and gravitational wave detectors. It is a process of constant refinement. If the simulated light curve is too blue or fades too quickly compared to the real one, the physicists go back. They adjust the equation of state, tweak the magnetic field strength, or modify the neutrino physics in their model. They run the simulation again, seeking a closer match. Each iteration is a step toward a more complete rulebook. These digital laboratories are where we test our deepest questions. What happens if we input an equation of state with a quark matter core? How does the light change if the magnetic field is 1,000 times stronger? By comparing the library of simulated outcomes to the growing catalog of real events, we slowly reverse engineer the conditions of the impossible, translating the universe's violent experiments into a language our computers and our minds can begin to comprehend. The symphony of data we currently hear is just a faint whisper of what is to come. Our cosmic laboratory is about to receive a monumental upgrade, a new generation of instruments that will not just detect these events, but will listen to them in high fidelity and see them with unprecedented clarity. This next wave of observatories will transform rare, singular cataclysms into a routine catalog of experiments, allowing us to study populations of mergers and finally write the definitive rulebook for matter. The future begins with a new era for the cosmos. Ground-based detectors like Cosmic Explorer in the United States and the Einstein Telescope in Europe are designed to be vastly more sensitive than our current facilities. Imagine moving from listening to a symphony through a closed door to having a front row seat. These observatories will hear gravitational waves from neutron star mergers across almost the entire observable universe, detecting not just a handful each year, but potentially hundreds. This sheer volume of data is revolutionary. Instead of analyzing one event in isolation, scientists will be able to compare and contrast dozens of collisions, looking for patterns. They will see how the properties of the merging stars, their masses, spins, and the resulting kilonova brightness vary across cosmic history. This statistical power will allow us to move from asking what happened in that one event to asking what is typical, what is possible, and what is forbidden by the laws of physics. But our new ears will also listen to a different part of the gravitational wave spectrum entirely. The Laser Interferometer Space Antenna, or LISA, is a future space-based mission that will detect low-frequency ripples in spacetime. While ground-based observatories hear the final, frantic chirp of the last few minutes before a merger, LISA will hear the opening movements of the symphony. It could detect a binary neutron star system years, even decades before they finally collide. This would provide an extraordinary early warning, giving astronomers a precise celestial address and a countdown clock to the ultimate cosmic experiment. We could train every telescope we have on that patch of sky, watching for the precursor signals theorized about, capturing the very first flicker of light from the kilonova, and observing the entire event from its quiet prelude to its explosive finale. Our eyes on the sky are also evolving. The Vera C. Rubin Observatory, with its gigantic mirror and enormous field of view, will scan the entire visible sky every few nights. It is designed to find change, to spot the new points of light that were not there before. It will discover kilonovae by the dozens, many of them too distant or faint for current telescopes to study in detail. For the brightest and most intriguing of these events, we will then turn the most powerful eyes in history toward them. The James Webb Space Telescope, with its unparalleled infrared sensitivity, can peer through cosmic dust and dissect the light from these distant forges with breathtaking precision. It will read the spectral fingerprints of heavy elements in mergers that occurred when the universe was only half its current age, tracing the production of gold and platinum across cosmic time. And on the horizon lies the potential for a third messenger to join this chorus: neutrinos. These ghostly particles, produced in staggering numbers in the hot heart of a merger, carry information about the most extreme thermodynamic conditions. Next-generation neutrino detectors, buried deep in ice or under the sea, may one day catch a burst of neutrinos from a nearby collision, providing a direct probe of the remnant's temperature and composition milliseconds after impact. Together, this network of next-generation observatories will create a multi-messenger web of unprecedented sensitivity. We will no longer be lucky witnesses to occasional cosmic experiments. We will be systematic scientists, gathering data from a vast laboratory where the universe continuously runs the same impossible test under slightly different conditions. Each new detection will be a data point, and with thousands of points, the true equation of state for matter will finally emerge from the noise, not as a theoretical guess, but as an empirical fact written in the collisions of dead stars. Despite the flood of data, the cosmic laboratory still guards its deepest secrets. The true nature of the matter forged in these collisions remains a landscape of profound unknowns, each unanswered question a frontier for the next generation of cosmic experiments. The first and most pressing mystery lies in the fleeting heart of the collision itself. What is the definitive nature of the post-merger remnant? Does it always, even briefly, become a hypermassive neutron star, or do some mergers collapse directly into a black hole without that intermediate step? The distinction is not just academic, it dictates the energy of the kilonova, the strength of the gamma-ray burst, and the specific blend of elements created. Detecting the faint, high-frequency gravitational wave ring from such a remnant is the key. A direct listen to the vibrations of this impossible object that would tell us if it is ringing like a bell or has already fallen silent behind an event horizon. Closely tied to this is the question of phase transitions. We have theories about quark matter cores and Hyperon soups, but what is the exact threshold density where matter fundamentally changes its state? Is there a sharp boundary inside these stars, a definitive density where neutrons dissolve, or is the transition a gradual blending over a range of pressures? The answer is written in the equation of state, but we need more precise measurements to see the subtle kink in the curve that would signal matter's ultimate transformation. Another great unknown is the invisible architecture of magnetism. What is the origin and true impact of the pre-merger magnetic fields these stars bring into their final dance? Are these fields fossil remnants from the original star's collapse, or are they dynamically generated and amplified during the inspiral itself? Their initial strength and geometry are wild cards that could explain why two seemingly identical mergers with the same masses produce kilonovae of different brightness or gamma-ray bursts of different power. Without understanding this magnetic blueprint, our picture of the cosmic forge is incomplete. Finally, there is the grand cosmological question of the R process itself. What is the full chemical yield of these collisions across cosmic time? We have seen one merger produce heavy elements, but is this the only way the universe makes them? How efficient is this process, and did it produce enough gold, platinum, and uranium early enough to seed the first generations of stars and planets? To answer this, we need to find mergers in the ancient universe, to measure the spectral fingerprints of heavy elements in galaxies billions of light years away, and to build a cosmic inventory of where the elements in our own world truly began. These are not small puzzles, they are the driving mysteries that define the frontier. Each one represents a blank space in our rulebook for matter under impossible conditions. And with every new chirp from the depths of space, with every new flicker of light from a distant galaxy, the cosmic laboratory offers another chance to fill them in. The collisions are not just events to catalogue, they are profound questions posed by the universe itself, and we are only just learning how to listen for the answers. The atoms forged in those violent collisions did not remain adrift in the void. They became part of the galaxy's great recycling system, the raw material for everything that would come next. This cosmic forge, operating under impossible conditions, did more than create exotic states of matter. It laid the literal groundwork for worlds like our own. The heavy elements synthesized in a Kilonova's expanding cloud, the gold, platinum, uranium, and even iodine were eventually swept up by the gentle pull of gravity. Over billions of years, these atoms became incorporated into vast molecular clouds, the stellar nurseries where new stars and their planetary systems are born. Our own solar system condensed from such a cloud over 4.5 billion years ago, a cloud that was already enriched with the stardust of countless generations of stellar lives and deaths, including the precious debris from ancient neutron star mergers. The iron in our blood, the calcium in our bones, and the oxygen we breathe were forged in the cores of massive stars that died in supernova. But the rarer, heavier elements, the ones that define so much of our technology and even our biology, have a more specific and violent origin. The gold in a circuit board, the platinum in a laboratory crucible, and the uranium that powers some of our energy, all carry the signature of a cataclysm that occurred long before our sun ignited. Even iodine, a crucial element for thyroid function in complex life, is believed to be primarily produced by the R process in these mergers. This means the violent death spiral of two stellar corpses, an event of unimaginable density and heat, is indirectly linked to the chemistry that makes our biology possible. It is a profound chain of causality where the most extreme physics in the universe sets the stage for the emergence of planets and, potentially, life. Without these collisions seeding the galaxy with heavy elements, Earth would be a very different place, likely a rocky world devoid of the complex geochemistry and mineral diversity that drove planetary evolution and provided the raw ingredients for life's emergence. The copper in our electrical wires, the silver in photographic film, and the neodymium in powerful magnets all trace their lineage back to the furnace of a kilonova. This connection forces a shift in perspective. We are not just distant observers of these spectacular events. We are, in a very real sense, their legacy. The matter that makes up our planet and our bodies has undergone an epic journey, from the Big Bang to the hearts of massive stars, through the unimaginable pressure of a neutron star merger, across the interstellar medium, and finally into the nebula that birthed our solar system. Studying these collisions, therefore, is not merely about understanding exotic states of matter or the behavior of gravity. It is about reading our own cosmic genealogy. It is about uncovering the violent, beautiful, and impossibly dense processes that assembled the very elements from which everything we know and are was built. The universe's most extreme laboratory does not just operate in isolation. Its experiments write the elemental recipe for future worlds, connecting the physics of the impossible to the story of our own existence. These cosmic forges reveal a universe that is both violent and deeply creative. Neutron star collisions stand as the ultimate natural laboratories, places where matter is subjected to densities, pressures, and gravitational forces we can never hope to recreate on our own planet. They are experiments on a galactic scale, testing the fundamental rules of physics under truly impossible conditions. Through the convergent power of multi-messenger astronomy, we have learned to read these events in their full complexity. We listen to the ripples in space-time that chart the stars' final dance, and we watch the light that carries the chemical fingerprints of creation. Each signal is a piece of the puzzle, a different perspective on the same cataclysmic truth. Every new detection, whether a faint chirp from a distant merger or the precise spectrum from a fading kilonova, refines our understanding. It crosses out theoretical possibilities and brings us closer to the single, elegant equation of state that describes all matter at its absolute limit. This journey is far from over. The next generation of observatories, both on the ground and in space, will soon open their eyes and ears wider than ever before. They will transform these rare cataclysms into a routine catalogue of cosmic experiments, offering a flood of data that will finally write the definitive rulebook for the impossible. The universe's grand laboratory is always in session, and its next great discovery is waiting in the silence between the stars.